All right. So welcome back, everybody. Any questions before we get started? Have you figured it out?
Yes, it's long card.
What's that?
It's long card.
No,
No,
no.
it's not. Wait, it's Lupin.
Yeah.
So there we go.
Yeah. How many of you have read Harry Potter? Not many. Okay. Yeah. I mean, I'm hoping you get the reference. This is a defense against the dark arts class. So. All right. So let's get started. Any questions about the logistics or things that we discussed so far? Everybody enrolled in CampusWire? Right. Okay. So today I want to continue talking about some of the principles that we started talking about last lecture, and then also give you an overview of when we are talking about system security, what are the challenges, what are different basic blocks, and so on and so forth. All right. So last time I talked a little bit about logistics as well. I'm thinking about, I think it's quite clear for everybody. But if there's questions, feel free to ask on CampusWire. I created a paper reading list. You should find it on the schedule on the website. If you click on it, you'll go to another Google Doc and see the list of papers for each week. So I just left the week 10 paper reading list open, but because usually based on my past experience, I've seen some topics are more interesting than the others for some people. So depending on the demands and popularity, we will add some papers on the last week, because week 10 would be mainly review, so we probably have papers on different areas there. Okay. So what I'm gonna do is I'm gonna post a Google form sometime tomorrow. I'll let you know exact time. You have to actually go and select like up to 5 papers if you want to present. If you are teammates with somebody else, you can just put your teammate's name on the Google form. Or if not, you just select your papers and I'll just team you up with someone else. All right, any questions? Cool. So last time we started talking about what is security, right? And we said that essentially security is this achieving some sort of properties in the presence of an adversary, right? So we said, for example, only this user can read this file, or only this group of users can read this file, and so on and so forth, right? The main 3 goals of security, as we said last time, was confidentiality, integrity, and availability. We said that there are some other things that are kind of relevant to security, but not essentially security. The main 2 ones are privacy and authentication, which we're going to talk a little bit about in this course. But there's also other metrics such as reliability, fairness, and explainability, which is also very important, but we're not going to discuss it that much in this course. So then now we know that what we are trying to achieve and what are our goals. The question really is that, I'm recording. Okay, yeah. So the question really is that how do we achieve security? And we said that essentially we need to define some policies and then kind of implement those policies and enforce those policies in order to achieve the security that we want. The 2 main issues with policies that we need to implement and enforce them. And as I said last time, what we're going to see is that both this implementation and enforcements are not ideal. And as a result, it will introduce some additional problems. So in theory, the policies are working and are good. But in practice, when we are implementing these policies, they're not perfect because of multiple reasons, because of the complexity, because of the bugs, because we didn't think about it thoroughly, and so on and so forth, that this implementation itself has some problems that we're going to fix. And in fact, most of the security problems that you have these days are not because of bad policies, but it actually is because of bad implementation or bad enforcement, unfortunately. Right? So this is actually by itself is a big challenge. And then, as I said, and next steps is not just enforcing and implementing these policies. Unfortunately, we're living in non-ideal world, so we need to be able to react to potential attacks as well. And this reaction has to be in form of first detection, obviously, and then once we detect, we need to be able to quickly, make a decision, make adjustments. So, for example, I talked to last lecture, I talked about NotPetya as one examples of a real-world malware. And there I told you that, quickly Microsoft and companies try to patch it, right? So, I mean, timely reaction is also very important in this scenario. Okay, so, and then we said, okay, how do we define policies? And now we need some policies in order to achieve security. How do we create those policies? And what we kind of started last lecture and we didn't really finish it was some sort of security principles, some sort of rules or laws, if you want to call it. That some of them are based on some hard theories, some of them are not. It's mainly both based on the experiments that people have done and years of working on this domain. So what are they? The first one, as we said, was threat model. Basically, threat model is just a list of assumptions that we have about the victim's capabilities and the attacker's capabilities. And we said that these are just basically assumptions. It's not something that we can prove most of the time. So as a result, we have to be as holistic and as accurate as possible. And also, it's kind of like something that's it's kind of based on your assumption you can provide security. So you can say, for example, that I'm assuming that these are the capabilities of the attacker, and under this assumption, our system is secure. Well, what would happen is if the adversary managed to get better, capabilities, and as a result, that adversary might be able to break the system, right? And that would be a challenge, and that would be a problem, but it's just the way it is, right? So here are some of the questions that we ask. I'm not going to go through them again. And then on the victim side, again, the same type of questions. What can be trusted is also another very fundamental questions on the victim side, and we're going to actually talk more about this in this lecture. Sorry, be careful about your the other one. I mean, if you want, you can move to the next one. Anyway, so the second thing was the overheads, and we said that the problem of cybersecurity is extra challenging because we're not only trying to solve the problem, but we also need to be very careful of other important metrics. And unfortunately, for a long time, we kind of be very cautious about security and trying not to really mess up with other important metrics. And that makes the problem even more challenging. And then the final thing that I discussed last time was the multi-layer defense or defense in depth. So really the idea is that instead of having just one roadblock in your system, the best thing to do is having multiple of this. Some of them might be more sophisticated than the others, but the idea is that usually it's not a good idea to have something very powerful, but only have one of them. And the entire system will be compromised by that. Because one way or another, the attacker might find a way to circumvent that. But just if you have multiple of them, the chances and the odds that the attacker can, compromise all of them would be very, very low. So usually it's a better idea to have a multi-layer defense system. And that's what we usually do. We have defenses at the software level, at the operating system level, at the hardware level, and so on. Any questions so far? Okay. So let's continue talking about this. That's the fourth principle that we need to be careful about and know about is what's called the principle of least privilege. The idea of principle of least privilege is that we need to give permission to a specific user or application just as much that that specific task can be finished. So for example, if you have an application that play music, that application only needs to access our speaker, right? For example, in our cell phone. It doesn't need to access our camera. It doesn't need to access our contact and anything else, right? So we give the least possible amount of privileges, least possible amount of accesses, so that specific application or that specific user can finish its job. Think about a building, for example, if there's somebody who wants to access this room, the best thing we can do is that, have a lock for every single room and only give access for that person to this room, and all the other rooms are locked, right? And of course, this is kind of challenging because we need to identify what are the resources that user or that application needs and then give that to them. But it's something that we always need to be sure that, we always give the least possible amount of privileges to a specific user or a specific application. On computer systems, it's very common that we usually have at least 2 levels of privileges. For those of you who kind of have some backgrounds in operating system, will probably know that. So we usually have user level and root level. So the root level is the one that has access to actual hardware and all the firmwares and all the IOs. And the user level is just have some bare minimum, level of access. In some systems, we have multiple of them. So we have a machine level as well, for example, and so on and so forth. But typically what we do is that for every application wants to run something, we only give access at the user level. If the user level have some privileges, including, for example, the root password, then they can escalate their privilege to the next level and next level. And this way we're kind of protecting systems. So for example, user level cannot access certain libraries or certain files in our system and so on and so forth. You probably know this already. For example, if you're trying to install something, if you're not a root level, you cannot really, or in Windows, for example, admin level, you cannot really install this, right? So that's the idea, that even if something is compromised, at least we can contain that compromisation, right? So we don't let it to move forward and spread itself. Any questions here? The fifth one is what's called a distributed trust. So the idea is that we shouldn't give, put all of our trust in one single entity or one single file or one single user. We actually, if we can distribute the trust into multiple people or multiple users, that increases the security. So for example, the main example here is usually like, in military systems, such as missile systems or nuclear systems. So usually there's not only one person can authorize this, it's usually multiple people have to, they have their own keys and they have their own authentication codes in order to let, the system get activated. So because of that, you can think about, if one of these people are compromised, either their identity is stolen or they have, become all of a sudden malicious, still we have, multiple people who kind of, prevents, a disaster or attack to happen. So distributed trust is actually one of the key ways of protecting systems, especially in more critical systems such as, industries or military systems or governmental systems. All right. The sixth one is what's called ensure the complete mediation. So what happens is, for example, if you have, a system that has multiple different entries, what you need to make sure is that there is no single one that is kind of like less secure than the others. So what you need to do is that making sure that every single one of them has the same amount of, security level defenses and so on. Because, for example, what people often do is that they have, for example, think about this room, you put very good and high quality locks on your doors, but you forget about your windows, or maybe one of your windows is kind of like not great in terms of security and the others are great. And unfortunately, the problem is that you're only as good as your weakest link, right? So you have to make sure that any sort of solutions or any sort of security mechanism that we have, it's a complete scenario. It includes every single possible entry to your system, every single scenario that the attacker can attack your system, and so on and so forth. So being complete is a key here. So you have to make sure that, again, it's kind of similar to multi-layer defense in some sense, but here we are saying that, at each level, we also have to make sure that we have equal amount of distribution of, attention to all of possible entries to the system. And another one that people typically make a mistake about is you cannot achieve, or you should not achieve security but by obscurity. What does that mean is, you cannot say that I have this secret algorithm that, for example, encrypt my data. Everything about your algorithm has to be known, and everybody has known about it, including the adversary. And the only thing that has to be, kept secure is maybe some information that you want to protect, like secret key or secret data or whatever you want. The way that you achieve security should be known to everybody. So it's not, there shouldn't be any secret algorithm that you use. And the reason for that is keeping specific value or specific secret is easy, or at least it's doable, but keeping the entire algorithm secret is not doable, because there are many people who are actually working on that, and the chance that that can be, leaked out is much more high, right? So in most of these security systems, the algorithm for using the system secure is publicly known. So for example, all these, high quality and standard crypto systems, including AES or RSA and so on and so forth, which we're going to discuss a little bit about. All of them, all the algorithms, including the code, all the steps, everything is completely known. You can actually look at it online, and you can actually change it if you want. All right. So the security actually comes from the fact that the adversary knows everything about our algorithm, about every step that we take. The only thing that the adversary does not know is some secret value or some secret key, right? And the entire security actually built off from this assumption. And that's really powerful, way of securing systems, because we're not really relying on the fact that the system is obscure in some way or shape, right? This is also known as Kirchhoff principle, or sometimes Shannon maxim. So the Kirchhoff principle also saying that, especially for crypto systems, the only thing that has to be remain secure is the secret key, and everything else has to be public thing, right? So whenever you're building a system, don't rely on obscurity in order to achieve security, right? Just assume that everything about your algorithm, everything about your code is publicly available to everyone, right? Any questions here? And this is very tempting. So if you ever, doing some projects about your security, you've probably seen that, the very first thing that people think about is, maybe somehow doing something magical that nobody else knows, and maybe this way we get security. But that's not the way to do it, all right? Okay, so this next thing is what's called using fail-safe defaults. So the example of this is, again, locks on the doors. So for example, imagine that, we have card readers to open every door in the building. And now imagine that the power is gone, right? So the card reader doesn't work. Now we are in the fail-safe, in the fail state. And now we should decide that on the fail state should be like, by default, make all the doors unlocked, or should we make all the doors locked, right? And in terms of security, you should always make sure that on the fail status, your system has to be safe. So in this case, your system has to be, all your doors or everything has to be locked. So in other words, if the system for some reason does not work, for example, if your system is not powered, or your computer system does not do the monitoring and all this stuff, you have to make sure that the default state is the safe state. It's the state that doesn't allow anybody to enter your system. So for example, if you have a network controller that checks password authentication, and for some reason that the network is off, you shouldn't allow everybody to let in and come in and log into your system, right? Everybody should be failing to log into your system. Of course, this would be a convenience issue, because once the power gone or a network is gone, nobody can actually access the system. But in terms of security, this is the right decision, because at least doesn't allow anybody, including the adversary, to go and use your system, right? Any questions here? The second thing, the next thing is isolation. So usually most of the systems, both software or browser system or hardware system, typically use isolation. So when we are building our systems, for example, our processors, we have multiple different processes, right? So maybe one is checking your email, the other one is playing some music, the other one is open a Word document, and so on and so forth. So you have multiple of these processes, right? And what we should do is making sure that these processes are only work on isolation. So in other words, this process can know nothing about this other process or this other process, or cannot impact in any shape or form the execution or the data or any sort of activity that the other processes have. So everything that we do has to be in complete isolation. This is the same story for example, multiple tabs in your browser. So if you have multiple tabs in your browser, the idea is that this tab, everything about this tab has to be completely isolated from this tab. All the data, all the code, everything. So basically, this tab has no idea that what's going on in the other tabs or the other tabs and so on. So we usually just make things isolated. And as we're going to actually discuss in this course, once we talk about hardware a little bit more, you'll see that how actually we achieve this with the isolation. But that's the important part of the system. And finally, the last thing is you should achieve security with simplicity as much as possible. It's kind of like also related to obscurity. But here is saying that if there are two different methods in order to achieve security, the best thing to do is use the simplest possible method. And the reason for that is that then, remember I said the enforcement and the implementation was the challenge. That's exactly because of this. Because if the system is so complicated, the chances that somebody who's implementing this or somebody who's enforcing this make a mistake is much more higher compared to when your system is very simple. So you should try to come up with the simplest possible, methods for your security system in order to, avoid this kind of, errors in implementation or in the enforcement. All right. So here it is. This is your list of
Question about the security part.
Uh-huh.
So you said that you do not want to keep your the security algorithm complicated. And you also you want everybody to know what the secret key is.
No, not the secret key. You want everybody to know your algorithm, not the secret.
Okay, so I'm wondering does it that completely the distributed part where you would want certain people, only certain people to know certain things?
But that's about the secret part. So distributed trust basically saying that instead of having one key, maybe it's a better idea to have multiple keys. And your algorithm takes all these keys in order to, for example, encrypt something or decrypt something.
Oh, okay.
So still the algorithm is known to everybody. The secret part can be distributed among people. So partially known by everybody. All right, so here's, as I said, here's a list of the principles. Again, there might be some additional things that you might see somewhere else, but these are usually, the most, very comprehensive list of security principles that you usually do. All right. Okay, so what are the challenges? As I said already, the implementation is the big issue. So again, these principles are good in theory, but unfortunately, when it comes to implementing these ideas, we are facing issues. You either have fundamental implementation issues, or sometimes we just have bugs. Similar to the way that we have bugs for normal software, when we are trying to implement something security related, we might also have bugs. Okay. Another problem is what's called a zero-day attack or unknown attacks. So the zero-day attack means that something that's when we are designing the system, the attack or the vulnerability was there and we have no idea about. We're gonna have lots of discussions about this and lots of examples about this. So for example, there is this thing called side channel attacks, where essentially people can by some activity they can know what you're trying to do. And this is not something that, when we were designing the systems, we know about it. It's something that is always there from day zero. And because of that, no matter what principles or what security mechanism we use, we're always vulnerable to the systems. And this unknowns or zero-day attacks is kind of some things that we need to just explore our systems. We need to think more about systems. We need to understand our system better in order to be able to detect those. And there are some people who are kind of white hacker or blue hacker, if you want to call it, that's their job is basically this, that trying to find this, is there any new vulnerability? And if they find something, they, patch it. So they don't, they don't hack the system in order to attack it. They hack the system in order to know what are the 0-day vulnerabilities on the system, so they can quickly find it and patch. So it's kind of like an arm race between attackers and defenders. Whoever finds it first, they can win. All right. Another challenge, as I already discussed as well, is the overhead or the complexity. So all of these things that I mentioned is great, but unfortunately, most of them come with some overhead. So for example, if you want to distribute trust, it probably needs some sort of round of communication. It needs some more storage and so on and so forth. So this means that the systems becomes more and more complex, and that's definitely not what we want, right? The fourth one is the large attack surface. So the systems, unfortunately, that we are dealing with these days is very, very complex systems, right? You can attack in multiple different software. You can attack at the network level. You can attack at the operating system level or at the hardware level. And we are dealing with something that has a really large attack surface. So think about that. You want to protect these doors, but you have hundreds of doors in this room instead of 2 doors, right? So the chances that the attacker can, penetrate in one of these doors is much more higher. So we're dealing with very large attack surface, unfortunately. And finally, these policies may not be correct or at least adequate. So there could be some things that we are missing when we're designing something. So it's also very possible that there is a chance and there's a problem there. So implementation and enforcement usually the main issue, but sometimes the policies itself might not be correct policies. Okay, so we're going to talk about these more in terms of actual systems. So this is more of like general ideas of how to make the system secure, but we're going to actually give examples in terms of real systems and real attacks, so you see how this actually connects to the real world. All right. Okay, so now I want to talk about the computer systems and the world we live in, the current status, and then finally I'm going to talk a little bit about how do we start the trust in our system. So the world we live in these days, as I'm trying to show and convey in this picture, has completely changed since maybe 10, 20 years ago. We are surrounded by computers in many different scenarios, right? And the current state of the cybersecurity is, according to a recent report by Microsoft, in 2021, the cost of cybercrime worldwide has been estimated to be somewhere around $6 trillion. The cybersecurity spending in government and in large companies in order to prevent this type of attacks has been around $1 trillion. And according to Microsoft, there has been 11, and the average time for attacking one server somewhere, mainly Microsoft servers, have been 11 seconds on average, right? So this is how frequent we are facing this attacks. Various types of attacks, obviously. And the current status quo has been, unfortunately, we didn't mostly care about the system. So the reason for that is that we didn't really design for security. So we mainly think about other objectives when we are designing the systems. Then the main objectives that we really cared was performance, was energy consumption, and was cost. Okay. So if you think about systems, we always talk about those performance doubles every 2 years. The systems gets smaller and smaller, the cost goes down and down. And actually, we have been pretty successful in this, right? So if you compare our current computer systems compared to 20 years ago, 40 years ago, 60 years ago, we have been significantly successful of creating powerful computers. But unfortunately, security has always been the second objective. So we never designed a piece of software or an operating system or hardware with security as the main objective. We usually just try to optimize the performance of the processor or optimize the performance of the software. And we always, think about, okay, how about security? And maybe we added some things. But unfortunately, there's this reverse relationship between new features and security. And what happens is that as we add new features, unfortunately, the security goes down because we are adding more and more features. We make our system more complex, and we're also adding more attack surface and attack possibility to the system. And this is exactly the recipe for making the system less secure, as I described in the previous slide. So more features, more convenience, features and options to the system, unfortunately, results in less secure systems. And this has been the trend for past 20, 25 years. Okay. And this is kind of like something that's been recently changed. So we recently, given this, the most of these systems has been attacked left and right. And at the government level now, we see that cybersecurity can become a real dangerous weapon. Now you see lots of spendings at the government and state level about security, about education about security, and so on and so forth. And as I show in the past few slides, we now have around $1 trillion of spending on security, and the assumptions and the prediction is that this number is going to significantly grow. All right, so that's what we are facing these days, and now you see that as I said, this becomes an important topic, so much more interesting topic for many people to learn about. And the current strategy as a result of this, 20, 25 years, strategy that we have is we kind of like to do a whack-a-mole situation. So you kind of like, back and forth a game between the attacker and the defender. So as we're going to actually talk about real examples in this course, you will see that there is a new attack. There will be a patch or defense for it. The attackers look at this defense and coming up with a more sophisticated attack. There will be a patch for it, and there will be a new attacks and so on and so forth. So this is a story of 20 years of, for example, memory safety attacks that we're going to talk about, or about the processor. So this story, go on and on and on. And the main reason for it is, first, this is very complex scenario. And the second is that we really didn't design the systems with security in mind. So we kind of just, trying to patch things. And as we patch this one, this new one comes in and so on and so on. All right. Okay. And then to give you just one quick overview of trend in future and kind of done with, the stories we're telling about cybersecurity, we are facing two main trends in the next at least 10 years or so. The first one, we're going to see more and more devices, more and more competing devices. This is mainly fueled by what's called Industry 4.0 revolution, or the revolution of cyber physical systems. So we're going to be surrounded by these tiny devices that has very capable, that are very capable in terms of computation, and they have network connectivity. They can actually, communicate with each other and so on. So smartwatch, smart, devices in your home, autonomous driving, robotics, drones, all of these are the examples that we're going to see. In industries, there's actually even more. You will see, robotics arms, robotic systems, and in order to, boost and improve the productions of the system, right? So we're going to see more devices, and more devices basically means more opportunity for the attacks, right? So again, this is another report recently published that by 2020 we had around 200 billions of this devices, this connected devices, laptops, smart refrigerators, smart applications in our homes, so on and so forth. And the market cap is around $11 trillion. So by 2021, that's 2025. So that's the huge, how huge this industry is. The second issue that we are going to see, and we kind of facing it right now, is not only we have more devices, but this device is going to, control many critical systems in our life. Banking, manufacturing, education, retail, smart, transportation, and all these things. So we are going to see that more and more of these devices connected to each other and controlling lots of things that maybe 20 years ago you just go to your bank and check your account, but now you use your cell phone to check your account. So it's the chances and the impact of these attacks also going high. All right. So as a result, we're going to see that securing computer systems is going to be even more and more challenging. All right, so now we kind of like, enough about motivating and talking about the problems. Now let's actually go through actual examples, and from now on we can start talking about real examples going through the systems. In order to understand why we are learning about these things, I want to first give you an overview of the computer system structures. What are the basic elements, and what are the challenges in each of these elements? All right. So you can think about any computer system structure as kind of 5 main basic blocks. We have some sort of sensing or input I/O. We have some sort of local processing. Then we typically have some sort of networking between these devices. Some of this networking is also supported by some backend processor or the cloud processor. And we finally go to some sort of actuation. All right. So this actuation could be in the digital world. For example, you play a sound or something you hear, or it could be on the actual physical board. So for example, you move a robotic arm or your autonomous car like move and so on. So, all right. So the color that I'm showing here is that computer systems could be only this local processing part really. Most of the cases, this local processing is accompanied by some sensing and some actuation, either both of them or at least one of them. And in some cases, you might see also some network connectivity and some cloud communication and cloud activity as well, right? So your system could be just this, it could be these 3, it could be these 4, or it could be these 5 altogether, right? So it could be very complex systems of edge and cloud all the way, or it could be just your laptop, which is basically just a local processing. All right. So now let's actually go through each of these 5 different elements and talk a little bit about what they are and what are the security challenges in each of them. The rest of this course would be now going through each of them in more details, talk about real examples, real attacks, and real defense. Any questions so far? What's that?
What do the colors represent?
So the color, the black one is just, we always have it. Then the second tier, we usually have the orange one, which is the sensing and the actuation. And the blue one is for some things that we might not see very often, which is the network connection and some backend processing, which is the cloud.
These are like the same ways attackers can get into it.
Not the ways that the attacker, it's just the ways that we build our computing system these days. So think about all the computers around you. So your smartwatch, for example, is a local process, is a sensor, right? Is a local process. It has some network, it has some cloud, and that's it, right? So that's your, for example, smartwatch. Your laptop is mainly, I would say, a local networking cloud. But think about something like a robotic arm, which has sensor and it also has, actuation and so on. So it could be a combination of all these 5. Of course, the local process would be the main part, otherwise you won't have a computer if you don't have the local process. So when we have this, the question is, okay, what is the threat model in this scenario and what are the attack vectors? I'm going to go through them one by one. And unfortunately, to answer your question, basically the attack vector is basically all of the above. So at every single one of these instances, the attacker can infiltrate the system one way or another and change the system. All right, so the first thing we want to talk about is the sensor. So the ways that the system can be compromised essentially are 3 ways of compromising the system. The first is by changing the physical domain. So I was going to show you in the next slide. People, for example, have shown that if you have a machine learning system, a vision system like an autonomous car, people have found that if they actually add these tiny patches to the stop sign, they can force the system to make a wrong decision and think that this is actually a different sign, different traffic sign. And we're actually going to talk, when we're talking about machine learning security and privacy, we're going to show you how this attack is possible. But to just give you an overview of what we mean by changing the physical domain is this, that somebody can just add a small patch to your system and make your system to make a wrong decision. Another example is what's called a dolphin attack. So the dolphin attack is actually very clever attacks for this voice recognition system, such as your Amazon Alexa or Siri, etc. So what people have shown a few years ago and showed that is that if they, create some voice signal that is not in the frequency of, the frequency range that we can hear, so above 1.46 kilohertz, they can actually, they saw that, the voice recognition system can pick up that signal and actually analyze it, but we cannot hear it. And as a result, they show that, for example, they can create very clever signals, very clever commands that nobody can hear it, but the system can actually respond to it. And that could be a command to do something. So for example, people went to Subway and then create this, the signals, and they saw that, they can open, for example, specific messaging app on your cell phone of people that are on the subway. And you have no idea that your system is actually doing this because you cannot hear the command, right? So for example, you say, hey Siri, do this and do that, right? But what this dolphin attack does is basically doing the exact same thing, but in the frequency range that you cannot hear. So you have no idea that your system is being, right? So these are the examples of how we can actually impact and change our physical domain and force our sensors to make a wrong decision. All right. Another thing that can happen is that interfering with the sensing environment. So there are again attacks that I don't have example here, but shows that, for example, let's say that your camera is sensing something. They show that if you, for example, they shoot a laser to the camera, they can mimic the behavior of, for example, an obstacle in the system. So for example, there was this examples of a Tesla car that's going through on the road, and then somebody was shooting some lasers to the cameras of the Tesla, and the Tesla all of a sudden thought that there is an obstacle in this road, and they have to stop the car, right? So it's kind of like think about it as a denial of service type of attack, that we kind of like mess with the environment or mess with the sensing sensor, for example, the camera, and then force the system to make a wrong decision. And finally, another thing that usually people do is creating some sort of faults. Changing the physical environments and interfering with the environments can be considered as some faults, but there are actually real attacks that create some faults in order to achieve what they want in their system. This usually, for example,
What is the difference between the first two things, like changing the physical environment, just interfering with it?
So changing the physical environments means actual objects that are being sensed. The interference is with I should put sensors, maybe that's easier to understand. So we are trying to impact the actual sensor. So for example, if you're shooting a laser to the camera, the changing the physical domain is more of like, I just put some maybe sticker on the stop sign, and then we just wait for the sensor to pick it up. And what's happening right now is kind of a trend that we are seeing in the future is that we are seeing new sensing modalities and sensor fusion. So in the past, for example, we had only camera, or we have only LiDAR, or we have only our RF sensing signal. But now we are kind of trying to collect all of these. So for example, again, if you look at the autonomous driving as an examples of very complex sensing systems, they usually these days have cameras, they have LiDARs, they have temperature sensors and all these things. And they're to collect and fuse all of this information together in order to make a decision. And since these systems become more and more complex, unfortunately, there's now more opportunity for the attacker to also attack the systems.
I noticed that in your examples, it was primarily about machine learning for sensor security. Is it just because in sensor security, that sort of field, machine learning, or is it just
no, yeah. So these are recent examples that I gave you, but you can also, what you do as your backend could be machine learning, could be just a simple rule base.
Right.
Actually, the dolphin attack is not necessarily using machine learning, just use the basic speech processing and signal processing. So you can fool both of those systems. So the idea is that we are changing things here. We're not changing anything inside the systems. We are just dealing with and changing things in the physical domain. And the results, we are seeing that things are, the ultimate command is different than what we are expecting. Okay. But yeah, machine learning is specifically becoming more and more interesting and more important these days. And there is a specific field for machine learning security and privacy. We're going to actually spend about 2 weeks on machine learning security and privacy in this course as well, where we're going to talk about how it's possible to, for example, add a small sticker to your stop sign, and all of a sudden your machine learning or object detection methodology thinks that this is not a stop sign. So it's actually quite interesting as well. Any other questions? All right, so now local processing, the second thing is the local process. And as I said, this is like the core of the systems, the computer systems. We will talk a lot about lots of different things that can go wrong and can be attacked in a local process. Mainly, we're going to talk about the trusted booting, how the attacker can mess up with that, and how we can make sure that the system is not booting correctly. A large class of attacks on the local process, what's called a side channels attacks. We're going to spend about a week or two on side channels to discuss, describe it to you what is side channels and why it's important. Another basic class of attacks are fault attacks. So think about, for example, changing the voltage of your computer. And by changing the voltage of your computer, the system starts, not operating as expected. So what we are doing is changing the operating conditions of the computer. And as a result, the computer starts creating some faults. And that fault could be either, denial of service, or in some cases, the integrity of the system, or even worse, the confidentiality of the system. Another huge class of attacks that we're going to talk about is the memory safety or memory vulnerability attacks. So this is basically, if you've probably heard about things like buffer overflow, return-oriented attacks, and so on. This is very important class of attacks because it's essentially this is the interface between the software and hardware, and you will see that how powerful these attacks can be. Another class of attacks that you will see here is attacks to the energy systems or power management systems, essentially for those that are battery powered. Since these days we are having lots of devices that are battery powered, one type of attacks that can happen is just depleting the battery, right? So for example, especially think about medical devices, like something like pacemaker that somebody is implanted in the body. If the attacker managed to deplete the battery, it's actually very, very, very important, right? And finally, the attacks at the operating system or firmware level is also very important. We will very briefly going to talk about this and show that how the attacker can interact with the system. So the idea here is that the attacker at the digital world, there is a computer, and the attacker either interfacing with this computer or managed to run some process inside this computer. And as a result, can mess up with the confidentiality, integrity, or availability of the system. All right. And one thing that's very important to notice here is that local process, when we are talking about the local process, we are talking about a diverse set of computational power. Your PC is considered a local processing system. Your iPhone is also considered a local processing system. Your processor in your watch is also considered a local processing system. And because of this diversity, the challenges are also different. So in more, performance systems, such as your laptop, maybe you can run a more sophisticated detection or protection scenario. But in the battery power systems, you may not be able to run things that you would normally do in your laptop. All right. And we're gonna actually see that how this impact our system. Let's have a quick, maybe 3-4 minutes break, and then I'm going to talk about networks. Questions? We're good so far? All right. So the third thing that we need to be worried about is the network, obviously. So network itself is very, very established area of security. Actually, it's one of the things that when we start designing network system, we kind of a little bit care about security. So in terms of situation, it's a little bit better than the others. Unfortunately, in this course, we're not going to talk a lot about network security because network security is, requires really a course by itself. But to just give you some of the main challenges, the main thing that we really need to care about in network security is we want to have confidentiality, obviously. We want to make sure that when we are sending a message, only the sender and the receiver are receiving this message. We probably have heard about TLS and SSH as the most important ways of achieving security and confidentiality in network. Once we talk about cryptography a little bit next week, you actually gonna see how the encryption and decryption works, but we're not gonna particularly talk about TLS. Another important parts of network messaging is obviously the integrity. So not only you want to make sure that the sender and receiver are the only ones who are receiving the message, but you're also very worried about the message that you're sending to the receiver is the exact same message that you have sent, right? So the integrity of the message is very important. So there are lots of works on man-in-the-middle attack where someone tries to, in one way or another, change the message or change the integrity of the message. And finally, availability and authentication of firewalls, denial of service, identification of devices, and so on is like a very important topic in network. But as I said, we're not going to talk much about network security in this course. It's something that you have probably seen in 136. If you have taken the course or if you're going to take the course, you will see much more about this in that course. Some of the also newer and emerging challenges in networks, to just give you an idea, is the first one is, the distributed network. So these days we're not seeing, classical, one-to-one IP to IP, but we're also seeing, robots or devices or IoT devices that talk to each other. So we are seeing a distributed systems of IoTs, gateways, different protocols, such as, 5G, et cetera, that that makes the securing the networks much more challenging. And also these days you're seeing, if you, for example, heard about Amazon Sidewalk or these new technologies, and that trying to not only share the network, they're also trying to share their bandwidth. So for example, you can share the bandwidth of your neighbor if you have a technology such as Amazon Sidewalk. And of course, gives us lots of new services, very interesting services, right? But on the other hand, also brings lots of new security challenges. Questions? And also another thing that becoming very, very important these days on the network side is anonymity or privacy, like, making sure that, you are anonymous in the internet or in the network. Also relevant to networks is the web itself. So, as you know, web is a platform for deploying your applications and sharing your information. Typically, web is this interface between some sort of application, which we call browser, Safari, Google Chrome, et cetera, and some sort of computer somewhere else that connected to the same web, which is the cloud server or the server in general, right? And the importance of web security is also very high, mainly because this is basically the gateway between any sort of local device and any remote device, right? So usually the way of an attacker to infiltrate your systems, really the very first way is through the web, right? And the web is very powerful because web browsers can run applications, can access different files in your system and so on. So the adversary virtually has lots of power and lots of availability and lots of different knobs to play with in order to impact your system. You probably have heard about HTTP and HTTPS. You might have heard about same origin and cross origin, code injection, session management. These are the main challenge. Again, web security is usually part of the network security, which we're not going to talk much about in this course. Again, if you're interested, there are resources available. The thing that we do going to talk about is about the cloud and server. The difference between cloud and local processing is that they're basically the same computing system. So many of the attacks that we discussed on the local processing side would be applicable to the cloud or server. The one difference is that clouds generally is more attractive for the attackers, mainly because the impact that they have. So think about the cloud that controls a specific service for a bank or for Amazon Web Services or for specific retail and so on. The impact that we have by attacking those systems is much, much more than if we try to attack specific local processors, specific lab, right? So as a result, cloud and servers is usually the main target for attacking the system. So that's when we're gonna actually talk about them. And also, the impact is much more significant because there are lots of critical applications in that domain. So the challenge that we're facing is kind of like, I already discussed this, but because of the significant expansion of the web, cloud service and security of cloud services is becoming more and more challenging. And another things that kind of like make the cloud security much more challenging is this notion of platform as a service. So if you have heard about it, basically platform as a service, there are various, variant for this. This is infrastructure as a service. There is software as a service. There is machine learning as a service. So all of these is basically, there is some server, some computer somewhere in the cloud that you can rent. You can pay some money based off your usage, and then you can use it. So think about Google Cloud, probably some of you have already used, right? Or you can rent a specific node or computer on Amazon Web Services or Microsoft Azure. Those are all the examples of this platform as a service, where essentially there is a computer that you don't own and you don't have local access to. It's just connected into the web, and then you can just, using the web interface, you can access it. And unfortunately, this creates lots of security challenges, because if you can access this platform, it means that the adversaries also can access. And it means that, you might be potentially co-located with an adversary on the same physical platform. All right, so the major threats in cloud security, as we're going to talk about, is the co-location of many applications on the same hardware. And we're going to show specifically when we are talking about side channels that when you're co-locating things on the same physical hardware, what are the things that can happen? Unfortunately, when we were designing hardware, we never thought about this, but unfortunately, it's something that happens more recently, and now we need to deal with it. And then another thing that happened was the web itself wasn't really designed with security in mind again. And what happens is that, everything that we are doing now is kind of like a patching and fixing the issues that we haven't really thought about when we're designing the system. And one thing also relevant to the cloud is this new computation paradigm, which is the edge cloud. So what we are doing these days, if you probably have heard the term edge computing, is that we don't necessarily compute things on the local system. We usually, do partial computation on the local system, use the network in order to send the information to the cloud system. Why do we do that? Because as I said, we are talking about very tiny devices that doesn't have the computational power that we need. So for example, let's say we want to do something like an object detection on our watch. The watch that we have has battery power, doesn't have enough processing and memory for doing the object detection. What we can do is that using the sensors to collect that information, let's say the image or the frame, and instead of doing the processing here, we just send out the information and ship out the information to the cloud. And the cloud has this powerful computer and powerful server that does the computation for us. And it just sends us back the results. So for example, let's say we want to do the object detection, we send the frame, and the results that we get is lists of different objects with different locations, right? So this is kind of like what usually we call it edge cloud computing, where we virtually have the cloud communication, cloud computation power at our disposal, because we have a very fast network and we can upload things to the cloud, quickly compute things and get the results back, all right? And this is very, very interesting in terms of new capabilities. That's why, robotics now becomes much more powerful. That's now we can have, systems that are very tiny, but they have very strong and very powerful computational abilities. But on the other hand, this has also introduced new challenges. It introduced privacy challenges, introduced security challenges. And again, we're going to talk a little bit about these things in this course as well. Any questions so far? All right, and the last thing is the actuation. So think about the actuation as kind of like the interface between the computer systems and the outside world. If you think about our actuation and in terms of attacks, basically when we're saying an attack is happening, really what happens is that either some information is stolen, right? Some passwords, some data about, some sensitive data about yourself is stolen. Which, for example, UCLA is great at, giving away our information, right? So that's one example of, the information is stolen. But the other two aspects would be some sort of actuation aspect. Either some digital service has been impacted. For example, we attack a specific server and the server is down. So you can think about this as some sort of actuation, which, we try to get some service and the service no longer works. Or it can be also a physical actuation, real, physical and actuation. For example, think about, an autonomous driving car, a robotic system, a PLC, a medical device, so on and so forth. So if the attacker, for example, managed to shoot the laser to our system, what the attacker can do is that force our car to stop and thinks that there is that there is an obstacle, right? So the eventual goal of the attacker could be some sort of physical actuation or some digital actuation as well. It's not just stealing some information. This is one of the primary, goals, but the goal could be also some level of actuation. So we need to be very careful about the actuation. And as I said, we are experiencing more of this cyber physical industry evolution. We are more and more see this relationship between the physical world and the cyber world or digital world. And as a result, the impact the attacker can have to our physical worlds is much more high. A question? Another question? All right. Okay, so this is kind of the story of the computer systems. And then as you're going to see, we're going to kind of touch upon all of these things, excluding the network and web, which we leave it for another course that you might be interested in. All right. Okay, so the last thing I want to talk about in this lecture is the notion of trusting a computer. Okay, so now we know that there are these challenges. Now let's start with how we actually build computers and build a secure system. So like how we actually trust the computer. All right. How do you think we trust the computer? Any ideas? Anybody? What do you think is the procedure? What do we need to? So when we are saying the trusting the computer, what's the basic things that we need to do?
Understand what the computer does.
Understand what the computer does. Okay.
Who's had access to it?
Okay. But let's say we want to build, build a computer as a designer. What is the criteria that you want to have in order to build a computer, to trust the computer? What do you say that? How do you say that this computer is trusted and this computer is not trusted? That's the question.
Maybe based on like the way you encrypt the files on that computer.
Encrypt the files, but how do you know your encryption is actually correct encryption? How do you know that when you start your computer is not actually compromised at all? You know,
Maybe have
and
some kind of like check using some kind of encryption algorithm that lets you know that there's some kind of hacker who done anything with your computer before.
okay, so it's some sort of detection mechanism,
Yeah.
you say? Yeah, detection mechanism is important, but what about generally starting the computer with something secure? That's the question.
So you want somebody to verify that computer components or like the base level sort of firmware hasn't been modified?
Sure, you are really getting close. Yeah, that's a good answer. You guys?
I was going to say try and break into it yourself.
Yeah, sure. Yeah, you can do that too. Yeah. Okay, so we're kind of getting close to the answer. So we need to start the trust from somewhere. All right. So if you want to trust computer, we need to trust something. And using that something, then we need to kind of what's called a chain or bootstrap that trust all the way. And eventually we need to build this trust. We need to load our operating system, and then we need to maintain this trust. So that's usually what we do in order to trust the computer. To give you a little bit more examples, usually what we do when we want to use a computer is that we trust a specific hardware part of the computer, which is called the trusted platform module. It's part of the very tiny piece of hardware that we trust that this system has not been compromised and it's just designed correctly. How do we trust that? We usually trust the manufacturer of that TPM. All right. So we're trusting, for example, Intel or AMD or whoever makes this trusted platform module, that they actually correctly design this and give us the functionality that we're expecting. And the way that this trusted platform module has been created is that it's not something that the adversary can interact with. And as a result, the adversary cannot change anything inside. All right. So it's not something that is programmable. It's not something that gets any input from any user. So it's just a black box machine that doesn't have any inputs. It only creates some outputs. And it's something that has been created one time by a manufacturing company, and we trust that manufacturing company. All right. So we trust that. And that's the only thing that we trust in the entire system that we have. The rest of it is just this trick that we're going to discuss to securely boot our system. And as you know, booting means basically a sequence of activities that we do to eventually, load our operating system, which is a piece of software. And the operating system basically takes over at that point and control of the system. So when we're saying we trust the computer, we're basically saying that we start the trust from this trusted platform module, and then we have a sequence of boot sequence in some secure manner that we're going to discuss until we eventually load our operating system in some good known models, a good known state. And when we have that operating system, the rest of it is basically the operating system problem of maintaining that trust. And we're going to talk about that later on in the course. But so far, just imagine that we want to pass on something that we know that has been worked previously and has been secured previously, and we want to make sure that we are at that stage. Does that make sense? Any questions? Cool. And so then what we say, as I said, we start with this trusting this tiny module, this tiny hardware on system, and then we need to bootstrap this system. We need to change the systems all the way until we load our operating system. So let's see how actually we do it. So to give you an overview, I'm putting some block level diagrams of a PC. This is not the only block diagram that you might see in a computer system. It's actually something that you see normally in Intel PC processors. But for example, your watch or your cell phones has a slightly different system structure than this. What you're seeing here is basically a collection of CPUs. This is like a multi-core system. In this case, it has 8 CPUs. And usually there is some memories and DRAMs that are connected to these CPUs, and the CPUs are also connected to each other. The story of how we connect this and things like that is beyond this course. But the most important thing that you need to know about is this thing here, this platform control hub, which has this unit here, which is basically the beginning of the process of booting a system. All right. So how does it work? So basically, we are starting with, generally we're starting the boot sequence, and boot sequence, as I said, is just a series of programs to initialize different part of the computer. For example, if our computer has a network module, has inputs and outputs, has graphic, has different things, the boot sequence is basically going through them one by one, make sure that they are activated. And as I said, at the end of the day of this boot sequence, it will pass it on to the operating system, and the operating system takes over and control everything after that. What we want to make sure is that when we are doing this pass to the operating system, we pass it at somewhere that we can verify that this is a secure state, that we know that this has not been modified and there's no adversary active in the state. Then we pass it to the operating system. Of course, what happens after is very complicated things that we're going to discuss. But let's just start with this process first. So we start the trust, as I said, with this trusted platform module. This is literally a piece of hardware that we put in our motherboard. This piece of hardware is basically consists of two important things. A set of key pairs, the secret keys, that when we are building this hardware, we actually provision or put this secret information there. Think about it as usually somewhere between 256 to 1,240 bits of information. This is a long list, a number, basically, literally a number. And then we also put some cryptography functionalities, such as hash function and encryption and decryption. What these functionalities are, we're going to actually talk about it next week. But for now, just think about there's some high-level functionalities that we need in order to do our boot sequence. All right. And what we call this trusted platform module, or this piece of hardware that we start the trust from it, is root of trust, or ROT. All right. So generally in computer systems, in order to start the trust, you need a root of trust. All right. So you only need to find a way to have some sort of root of trust. When you have that, you need a mechanism for bootstrapping that root of trust to the next module, that you can use. All right. So generally, that's the idea of securing computer systems in any shape, in any format. Yes, the key is unique to every single hardware that we have. And the manufacturer knows what those keys are. Think about it as some sort of a database of this device that has this ID, has this key, and that manufacturer knows what that key is. As we're going to talk about later on, this cryptographic algorithms has a pair of keys. There's a public key and there's a secret key. The reason why we need both of these we're going to discuss next week. But the public key is actually what is shared between the user and everybody else. So the public key is actually public, it's available to everybody. The secret key is what remains on the hardware itself, and only the manufacturer and the inside the hardware knows what the secret key is. And in order to interact with this device, everybody use the public key to, for example, encrypt things and send it. And the secret key is the one that decrypts it. Again, we're going to talk a lot about this when we're talking about crypto algorithms next week. Any other questions? Okay, so we have our trusted platform module, which is basically a series of cryptography functionalities and some secret information. So this is basically our secret. Going back to what I just described, this functionalities is known to everybody. So everybody knows what are these functionalities. The things that nobody knows is this secret information, right? So if this secret is revealed, then this hardware specifically is no longer secret, right?
What aspect of these you can make it so difficult for attackers to attack them and how can we be sure that that information, like the key pairs, that itself can't be attacked?
So the trusted platform module is actually a hardware piece that is designed so that you cannot write things to it. So it's not a writable memory. It's a E2P ROM that's only read only. Okay, so it's a read only or ROM memory, right? So it's not something that an attacker can change things to. So there's something that's just burned into the hardware, and you just can read it. You cannot write to it.
Okay, so then in that case, if you can only read from it,
Mm-hmm.
how do you know that the attacker didn't mess with your system?
To read from it, it's possible. So it's actually the boot sequence can be attacked as well. But the way that this is designed is that the key will not be sent out of this trusted platform module. So it's not. So you at the CPU level, at the processor level, you cannot read these secrets. You can only pass your information there, and the encryption can happen inside the trusted platform.
No, no, no. What I'm trying to figure out is how this trusted platform module helps you, like, I guess, maintain the security of the system. So is this something like that you need to, if you're authenticating user, then you will actually like enter the key right there before you're able to access any browser system? Or how
No,
does
so you're not entering or changing anything. So when you're actually physically building this hardware,
that- Mhm.
you burn these values inside those read-only memory. So think about this as a piece of memory. Then when we are manufacturing the systems, we can write to it. But once we manufacture it, then we no longer can write to it. We can only read from it. All right. And then another things in addition to that is that it's not like, if you're a processor at the CPU level, say, oh, let me know what is this, for example, secret key is. The trusted platform module never gives you that information. It's only you can send information inside the TPM, and the cryptographic modules, whatever they are, is it an encryption or is it hash function or is it digital signatures or whatever, can actually do that activity for you and give you back the result. And as we're going to talk about cryptographic algorithms, if you see the inputs and the outputs of an crypto algorithm, you cannot break the system. So you cannot know what is the secret key. All right. So keep querying the systems with inputs and outputs will not let you know what is the secret key.
So
That's
before
the actually
you
main
like,
part of
you
the.
need to encrypt the data that you want to keep there. Just pass
You
it-
only see the plain text, the inputs, and the encrypted value, but you never see the actual secret key.
Okay.
Are we good? Any other questions? Okay. So how do we then bootstrap? So now we know that we have this semi-secure kind of like, fortress of trusted platform module. We have some secret inside it. We have some functionality inside it. How do we actually do the process, do the bootstrapping? And the answer to that is this idea of what's called attestation. All right. So attestation is generally this paradigm of sending some challenge and getting some response and see whether that response is what you're expecting or not. All right. So basically, it's the idea is this. So we trust the base, which at the beginning is just a TPM. We ask TPM or ask the base to compute the hash of the next blocks that we want to use. How does the hash is computed and why hash is secure is the question that we're going to answer next week. But for now, think about this functionality called hash that basically computes the content of this block and gives us a result, a value like X. And what we're going to do is that the TPM knows what the correct value of this hash should be. By correct means the value that is not being compromised. So because this is basically a piece of software, right? So we know that what this piece of software should be. We can compute the hash beforehand in the offline phase, and we can record this correct hash inside this TPM. What we're going to do is that during the boot process, we're going to ask the TPM to compute the hash of this function and compare this hash, this X, with this value that's been stored. If these two values are the same, it is guaranteed that this software has not been modified. It's the exact same software that we are expecting that it should be, which means that this software can be trusted. All right? The TPM can get inputs, right? It cannot give you, you cannot change things inside the TPM. That's the main criteria.
Can you give an example of this? I would understand what's going on with the.
Yeah, I do
base
have,
and this part.
so let me show it this way. So this is what we have at the beginning. This is our TPM, all right? What we do is that basically the boot sequence is series of different software. Think about it as a different function calls that we call one after another. What are these function calls is basically just one is for example, making sure that the IOs are known, one for loading the network and so on and so forth. We don't care exactly what they are, but just at the abstract level, think about it as functions, all right? So we trust this function. And what we do that inside this function, we ask that for example, we want to call function foo from function x, right? So inside this function x, we're gonna say that, okay, we're gonna call foo. What we're gonna do is that we're gonna say that this function foo is basically a series of instructions, right? What we can do is we can compute the hash of this function, right? And this gives us a value like h1, right? This h1, we also know that the correct format of this foo, the unmodified version of this foo, should be h foo, right? The hash function of that. That's one thing that the manufacturer who builds the TPM and who also builds the boot sequence gives us this ground truth information, right? So we also store this h foo inside our TPM, okay? So what we do is that this fx is gonna compute this h1, then it's gonna compare this h1 with this h foo, and if these two values are similar to each other, it means that the h foo is not being modified. So we can actually now trust foo as well, right? So we can now securely call foo and go to foo. And what would happen here is that we start with just very tiny piece of hardware, which is the transfer platform module. From there, we actually had a small piece of software here. From there, we called another software that is outside the TPM. It's actually stored in our main memory. So it can be modified and it can happen, many things can happen to it. But this way we are guaranteeing that that part of the memory has not been modified by the adversary, right? So you jump to this part of the function, and now this is also part of our root of trust. Okay, go ahead.
So at the beginning, does the TPM compute the hash of the first phase and then compare it with itself?
Compare it with the value that's been stored in the TPM as well. Okay, so basically TPM, as I said here, TPM has a set of keepers, some cryptographic function, and some secrets. Those secrets are these hash values. Okay. All right. So now this piece of software that is outside the TPM can now be trusted. And what we can do next, we can just repeat this process one more time over and over and over again. So we want to, from foo, we want to call bar. From bar, we call another function f3, f4, f5. We can go on and on and on, right? What we do need to do is that from every single function called to the next one, we first need to compute the hash function of bar, compare it with the value that we have stored for bar in our TPM, and then go to the next one, the next one, the next one. If these values are always unmodified, which means that this part of the memory can be trusted, we can load things from it, and we can continue.
So how does this work when you update firmware, say on a computer?
So you need to also update your hash values in your TPM. So there is very controlled process in the TPM that the manufacturer can also update values inside the TPM if needed. But that's a good question. One question here. Okay. So again, to give you, let me maybe I just. All right. So to give you an overview again, we have this tiny piece of hardware called TPM, which has basically this list of hash functions. Let's call it H1, H2, H3. It also has some key pairs, the secret key and public key, which we're going to talk about. It has this initialization software, which starts the boot process. And it has also some functionality for computing the hash function, right? At the beginning, when we are booting the system, we are reading things from this piece of software. The very first thing that this software does is that saying that, okay, what is the next function that I want to call? Let's call that PEI, which is the initialization of the DRAM. That part is actually stored in our regular memory. And this regular memory can be accessible by the adversary. So the adversary can change things, can break things, can modify things here. So we cannot just simply jump from the TPM to somewhere in the memory, because that's not a secure way to do it. What we need to do is that, okay, we say that this part of the memory is actually where this specific function is stored. What I'm going to do is that I'm going to use this hash function that I have here to compute the hash function of the content of this part of the memory. And then I'm going to compare this with this H1 that I've stored in my TPM. If these two values match, means that this part has not been compromised. It's the valid value that we are expecting to be. So I can safely jump into that part of the memory. Then if I want to jump and run another piece of software, another function call, I just repeat the process. From within this function, I compute the hash function of another one, which is, for example, this one. I compare that value with this H2. If they are matched, now this part of the memory can also be trusted, and I can go on and on and on until I reach to the point where the operating system has been stored, usually also part of the memory. I just compute the hash of the operating system. If that's correct, it means that the operating system has not been modified. I can load the operating system, and after that, it's just the operating system controller that controls it. Does it make sense? So a hash function is actually a function that gets line by line. So memory, think about the memory, think about instructions as some values, right? So there's actually, I mean, if you've taken some computer architecture course, you've seen that, basically instructions that have some opcodes and registers, numbers and stuff like that, right? So this is actually a value that stores in the memory. And if you change something into that instruction, basically some of this bit's going to be changed, right? So what we do is that the hash function, think about the hash function as a function that gets some, let's say, 64-bit value and updates the outputs, update this hash. And this just, it can repeat itself for every single line of the memory. And once we do that, we basically go through, let's say we want to access the program that has 100 lines. So we start with the beginning, go one by one, reach to the 100, to get a final value, and that's the value of the hash value of this function. Yeah, it's an actual literal value. Yeah, it's a literal hash value. So for example, remember, I mean, probably have you guys have seen when you're downloading a file, you get a value, your SHA file or your checkpoint file, and you can actually check that whether you have downloaded a correct file or a different file. It's called usually a checksum. The checksum is similar in some sense to the hash function. It just gives you the idea that whether this file is the same file that you have used before or it's not, it's something that's been changed. Does it make sense? Any other questions? Again, we don't care about these specific activities here. This is, if you're taking an operating system course, you're probably know a little bit more about the actual boot sequence and what happens at each of these states. But the only thing that we really care about is that we want to eventually run, load our runtime system, which is, if this is a PC, would be the operating system. If it's a more low-end system, would be a very simple runtime system. We want to reach to this point. And in order to reach that, we need to go step by step, all right? And this is kind of the summary of what we did. One question that some people ask is that why don't we put everything into our TPM, right? So what we can do is that instead of having this tiny piece of software and these hash functions, why don't we put just this entire thing into our TPM, right? And in that case, it is guaranteed that the initial version of the operating system has not been modified, right? We don't need to go through this hash function and this tricks that we do. The problem with that is TPM and manufacturing a TPM is very complicated and expensive task. And as a result, you want to have as small as possible of TPM as you can have, right? So what you do is that instead of putting all these different software, different firmwares inside your TPM and kind of, make sure that the system is secure, you start with very tiny one, this one, and then you only store the hash values of these different functions. And the hash value is a fixed, for example, 512 bits or 1,204 bits, something like that. It's very small value. So instead of saving this entire complex software inside your TPM, you're just storing a very, very tiny hash function, right? And this process of attesting and hash functioning and so on, it gives you the same level of security as you would have just stored everything inside your TPM. But you don't need to, store a bunch of things inside the memory of the TPM, because the memory of TPM is very, very expensive things to build, because you want to make sure that the adversary cannot mess with it, right? So that's the idea. You put everything inside your regular memory here. You only store very tiny things in your TPM and use this trick in order to make sure that the system is not compromised. Does it make sense? Okay. So yeah, so here is kind of like, the idea that what we do, this SHA-1 is actually the hash function. Again, we're going to talk about what is a hash function and how it works and why it's secure next week. But it basically, we start with some bootloader, we compute the hash, we put it here, we compute the hash, and we have, for example, the kernel, we put it here, we add this together with this as well, and so on and so forth. The reason that we put previous parts as part of the hash function as well is because we want to chain this, right? So we want to make sure that, not only we trust this previous function, but also trusted all the previous functions as well. So that's the reason that we not only just compute the hash value of this, but we put this with this that we have used before, and then, compute the new hash and so on. So we kind of like, first we have this function here, we compute the hash of this. The next time we compute the hash of this plus this. So the hash is, part of it is coming from here, part of it is coming from here. All right, so this way we kind of chain in this, that if somebody changed something, we still know that, we're trusting everything all the way. And we usually start with some initialization. So we start with some 0. So the very first steps, there's nothing before, so we start with 0. But then after that, we kind of chain this together. All right. And as you can see, this is actually this hash function that's been sent to the TPM, and then it comes back. So the TPM is the one that does the comparison for us. So still the hash values are stored inside the TPM. Okay. Any questions? Is that clear? Cool. So yeah, again, going back to here, where does this TPM stores, and how does it interface with the rest of this computer? Is actually, it stores here. It's called Platform Controller Hub, or PCH. All right. Again, this is a Intel terminology, so it's not, if you use an AMD or an Apple computer, it's not necessarily called PCH. PCH is basically has all of these different functionalities. But think about PCH as a separate processor with our main processor that is always on. So it's always listen to the power management, they always listen to our buttons and our system. And what we do is basically when we press restart or press the power, we are basically sending a command to the PCH. And PCH is going to talk to the TPM, which is part of this PCH, to start the boot process. All right. So when we start these things, the PCH basically calls the TPM, calls that software within the TPM, and then after that, the TPM basically takes over. Okay? And PCH, even if your computer is turned off, your PCH is still on. And that's why you can actually turn off or turn on your computer this way. Basically, your processor is off, but your PCH is on. And PCH is a very tiny thing that doesn't really spend too much power. So it's not something that's terribly, power hungry. It has all these other modules that we really don't care about for now. But the main things that we really care about is the trusted platform modules of this. All right. Any questions here? Almost there. And as I said, basically the bootstrapping process, PCH calls the UFE, which is the bootloader process, and the TPM. Then the bootstrapping thing happens, the bootloader process happens, the operating system takes over, and then you have a fresh operating system. You can start running your program, you can mess with it, and unfortunately, there are lots of attacks at that point. But at least up to that point, we know that the system is secure. Okay, so the question is, how secure is this? it's not something that's not possible to attack at all to the systems. There has been unfortunately attacks to the boot process as well. Usually the attacks to the boot process require some physical access to the system. So you need to actually be able to physically probe the system. But the remote access and remote attacks usually is not possible to the boot sequence. So I would say boot sequence is fairly secure in our systems, and that's why even nowadays you're relying on this process for loading our systems. So that's it with the bootstrapping. And so now that we have loaded the operating system, the question is, okay, now what? What should we do next, right? How we do run our applications on top of the operating system. So we have this operating system that has been loaded correctly, but loading the operating system is only half of the story. What you want to do is being able to run your applications on top of this operating system, right? At the end of the day, computer system is just something that you can run multiple different apps. So what would happen with this application? So obviously these applications cannot be part of the boot process. Why? Because this is a huge amount of memory that we are talking about, and we cannot really hash all of these values at the beginning of the boot process, because it's going to take, hundreds of minutes to actually, hash the entire, memory. So this application is not part of the boot process. The only thing that is part of the boot process is actually some part of the operating system, not even the entire operating system. It's only the kernel of the operating system is what we are really attesting. So the apps can be modified, the apps can be malicious, unfortunately, and all those things. So now the question becomes, okay, how do we securely run our app within the operating system, right? So how we run things in the operating system. And the answer to that is, so as I said, so first of all, we cannot really include those applications into our booting process, because the main reason is that they're very slow. Another reason is that they keep changing. So our applications are keep changing. And as I said before, in order to update the boot process, the TPM has to be updated. And updating TPM is not something that you yourself can do. The manufacturer has to do it for you, right? In order to prevent the adversary updating your file, only the manufacturer can update your TPM. So for example, just imagine that you install a new application and all of a sudden you need to update your TPM. This is definitely not possible, right? So you cannot include your applications inside the TPM. So you need to kind of find another way of running your application secure. How do we do it? I'm gonna wait for next week, or actually next week, to actually tell you how we do it. Because you need to first know a little bit more about systems, a little bit more about the operating system and cryptography before we are able to actually talk about it. But so far we are reaching to this point that we have a trusted beginning of the operating system, right? And now we want to run our applications on top of it, and we need to know how we do it. We still don't know it, but you have to wait. All right. Any other questions? Good. All right.